Let's design an audio filter to turn white noise into pink noise. Or at least try to get as close as we can. What is pink noise and why do we want to make it? Since we will be starting with a white noise source, we may describe white noise as static or a hissing sound. It sounds like it has a lot of treble presence because white noise has the same amount of power at all frequencies. And we hear in a nonlinear fashion, so our ears are generally more sensitive to higher frequencies, and we hear those more prominently out of all the frequencies present in the noise. Pink noise has a power spectrum where higher frequencies are increasingly attenuated, rolling off at about -3 dB per octave. Each octave span of frequencies contains the same amount of power, and with the gradual reduction in level, pink noise complements our hearing sensitivity as frequency increases, making pink noise sound more balanced in loudness across the audio frequency range. Although it's not a perfect correlation, look into gray noise for something that matches our ear's natural response a little better. Pink noise is sometimes called 1/f noise because its power spectrum is inversely proportional to frequency, meaning there's more noise power in the lower frequencies. This resembles the power spectrum of pink light, which sits near the lower frequency end of the visible light spectrum. With pink noise allowing all frequencies to sound well balanced to our ears, this characteristic is useful in audio engineering. It can be used when mixing audio tracks to help low-pitched instruments like bass guitars and drums sound balanced against higher frequency tracks. If the tracks each contain a certain frequency range of music, some tracks will need their levels higher or lower so everything sounds even. Comparing tracks against a pink noise reference track gives a good starting point. Playing pink noise in a room and recording it with a flat response microphone can help identify if the room's natural acoustics are causing some frequencies to get boosted or cut in the recorded sound, which can be fixed by EQing or treating the room for those frequencies. Another way pink noise is used is to create sounds that mimic nature. For example, if we apply more filtering to pink noise, like a wah-wah effect, we can accentuate or diminish certain frequencies and emulate the sounds of waves rolling in, or wind in trees, etc. So it's useful as a noise source in all kinds of audio applications. This circuit structure is commonly used as a pink noise filter network because a typical RC filter has too much attenuation. It contains 4 separate filter sections that shape the frequency response for different regions between 20 Hz and 20 kHz. Let's figure out how all the sections work and calculate the values needed to get this going. For a quick review on filters, when we calculate the cutoff or corner frequency or breakpoint, we're calculating the location of poles or zeros, which are the frequencies where a slope change of -6 or +6 dB per octave will occur on the magnitude frequency response plot. If there are multiple poles or zeros, their slope changes are combined for a net final slope. For example, in this high-pass filter, there's a 0 starting at 0 Hz, so we are increasing at 6 dB per octave. Then we run into a pole, which presents a -6 dB per octave slope change, and the net result from there on is a slope of 0, so we stay at that same level without attenuating or amplifying. Here's one stage of the overall pink noise filter, and this structure is called a phase lag compensator, normally used in control systems, but it provides a pole and a 0, and we get this response here. At a pole frequency, we start attenuating, then we get a 0, which cancels that attenuation slope, and we go back to maintaining a constant level. We can take advantage of the fact that as we approach each corner frequency, it's a gradual rounding off. It's not a sudden, sharp change. So what we can do is, if we bring the pole and 0 close in frequency, the gradual slope in one direction, and then the gradual slope in the other direction being really close together, we can control the overall shape of this slope. If we're trying to get -3 dB per octave for pink noise, we can tweak this, make a more gradual slope for a while, and then when it starts to level off and not do any further activity, we add another filter stage calculated to take over where the last one left off. And then we can just keep creating these customized slopes all the way from 20 Hertz up to 20 kilohertz, adding as many stages as needed, and then we're done. So let's give it a try using part calculations and then part empirical observations, taking advantage of being able to run a SPICE simulation, instantly see where we're at, and then just keep tweaking it until we're done. Looking at this phase lag compensator network intuitively, it's basically a voltage divider where we have two impedances instead of one in the bottom half, and one happens to be a capacitor, so it's frequency dependent. At low frequencies, a capacitor has a very high impedance and acts more like an open circuit, so there's going to be minimal attenuation on the output, which is what we see here at lower frequencies. Then as frequency increases, the capacitor acts more and more like a short circuit. The capacitor's impedance lowers until it's basically like a short circuit, so the voltage divider circuit attenuates the signal more and more as frequency increases, and when frequency is high enough that this capacitor is basically a short circuit, it acts like a fixed voltage divider with R1 and R2 and then a wire to ground, so we just get a constant voltage divider behavior at whatever attenuation level this would give as two resistors from that frequency onward. When a circuit is expressed as a ratio of its output to input, that expression is called a transfer function, and component values can be calculated from there to achieve the desired output, like the basic voltage divider circuit. In order to calculate component values for a phase lag compensator, we have to choose corner frequencies to place poles and zeros, then use the circuit's transfer function equations to calculate part values. The transfer function can be derived similar to the voltage divider equation by substituting in the impedances and solving for output over input. Once we have the transfer function expressed in a standard form, we can easily find component values associated with corner frequencies of the circuit using simple equations. I put the overall filter structure in LTSpice. Most of the values are just 0 because we haven't calculated yet, but we're going to start with this phase lag consisting of R1, R2, and C1, and we need to choose two values so we can calculate the third to get the response we want. So arbitrarily I chose R1 as 10K, and I chose C1 as 470 nano. I want to stay below 1 micro so we can especially stay non-polarized, and we need to keep the standard component values in mind when we're calculating and choosing values and substituting them back in. So with these two values, we basically have a low-pass filter, which I ran the simulation for, and here's the response. I have a cursor here that I can drag around if I want and see the exact values on this table. At a glance, I can double check here, am I within plus or minus 1 dB of my target minus 3 dB per octave slope all the way down. So I don't have to drag the cursor specifically every single octave every time I change a part. Since we need the filter to start doing what we want at 20 Hertz, I used SMath Studio to write in some equations to make all this easier. So here's the phase lag compensator transfer function. That lets us calculate resistor and capacitor values for this series resistor and then the shunt resistor-capacitor combination. So here, my starting values R1 is 10K, capacitor is 470 nano, and I need to figure out what R2 is going to be. And from the overall equation, if we rearrange the numerator zeros and the denominator poles, we end up with these equations to calculate where will the pole and zero of the phase lag compensator be with these three component values. But right now we're trying to calculate R2, and I happen to know I want a pole frequency at 20 Hertz to start rolling off. This here just lets me rough in some values. So if I enter a pole frequency of 20, and I enter my capacitor is 470 nano, so an R2 value for this would be 6.9K. And if I look at the table of standard resistor values, that would be 6.8K. So I'll enter 6.8K up here. And now this transfer function calculates the poles and zeros. So as we wanted, the pole is now at 20 Hertz. The 0 happens to be close to 50 Hertz, just because of these values. So now we come back to our actual circuit, enter in 6.8K, rerun the simulation, and there's our phase lag compensator. So now we start out with a low-pass filter response, but it can only attenuate so far, and then it just stays at that attenuation. So if we take our cursor, that's around 20 Hertz, so we've started rolling off and we're into our slope. And if we go around 50 Hertz, that's where we inserted a 0, so it starts to counteract the roll-off and go back to a flat slope, maintaining a certain amplitude. So now, to see where we are at, we can look at these values, and so our starting point is minus 2.3 dB, and the next octave up, we want to be 3 dB down. So that should be minus 5.3 dB at 80 Hertz. We're at minus 4.77, so that's within plus or minus 1 dB. And the next octave at 80 Hertz should be around minus 8.3 dB to be another 3 down, but it's not close enough to be within plus or minus 1 dB. We need more attenuation around 80 Hertz, and that's around here on the response plot. So we need to insert another pole somewhere to start bringing a roll-off back in, which means we have to now add in this second phase lag network. R1 is common, and then it's R3 and C2 that complete this phase lag network for this next frequency zone. While we have this single phase lag network set up, I experimented with changing R2 and the capacitor to observe how they generally affect the pole and 0 locations. We can refer back to this when we need to tweak the filters later. If we need more or less attenuation at a certain frequency area, we'll have a better idea which components to try to increase or decrease in value to tweak the response overall. So to insert another pole in our next filter stage, we might as well target 80 Hertz. It's all arbitrary for now, we just know we need another pole somewhere around here so that 80 Hertz will attenuate more. Since we can't change R1 and we don't know what capacitor value we need yet, let's just start from 470 nano on this stage as well. So we go back to our calculator. Down in this scratch pad, we're starting with the same capacitor, but now we want a pole at 80 Hertz, and we see that R2 would have to be negative, which means we can't really achieve this. So we need to change this capacitor value, and it has to go smaller in order to make R2 positive, as it turns out. I found that 180 nano finally gives me a positive resistor around 1K, so I'll enter those in and run the simulation. So now here's the cursor at 80 Hertz, and we inserted the pole, so we're continuing to roll off, and then later a new 0 kicks in and flattens out the curve again. If we go back to this calculator, we have 180 nano and a 1K resistor. So there's our pole at 80 Hertz, and the 0 is 884 Hertz. So that's somewhere up around here, and the 0 causes the response to go flat again. So this is what we're trying to do as we go, knowing that this circuit is eventually going to give us what we need because it's a proven circuit. So now if we look at the table here, now we're starting at minus 3 dB at our first octave, because every time we add another passive network, it may affect the whole response. So we always have to start over looking at 20 Hertz. So if that's minus 3, the next octave should be minus 6, and it's minus 5.9. The next one should be minus 9, and it's minus 8.4, so that's good. Then we should be at minus 12, another 3 dB down, but we're not quite there. So at 160 Hertz, again, we need more attenuation. So now we need to look at adding this third filter stage, and since we're doing this empirically, in the previous stage, we had good luck throwing a pole at the certain frequency where we needed more attenuation. So in this case, that would be 160 Hertz. To save some time here, I tried experimenting adding another pole for this third filter stage, and I reached a couple of dead ends, which is to be expected when just trying things out. As it turns out, targeting a pole somewhere around here, halfway between 160 Hertz and 320 Hertz octaves, is what worked best. One of the things I did, I tried targeting a pole around 230 Hertz, with a 56 nano capacitor, giving me a 2.2K resistor for what would be in series with the capacitor. And when I plug those into the transfer function, I'd have a pole at 233 Hz and a 0 up at just below 1.3 kilohertz. So if I enter those in and run it, this looked reasonable all the way up to 320 Hz, where each step was close enough to -3 dB starting at the 20 Hz level. But then 640 Hz started having too much attenuation. So that's somewhere around this part of the response. So this was just playing around with the poles and zeros, guessing where I might need to add a pole or a zero and plugging it into here to try and get the values. So over here, if I know I want to add a zero, for example, this area here is too steep. So if I bring a zero closer to here, it might cause it to roll off sooner and make this not as steep, and we'd be in spec a little longer. So right now we have a zero at 1291 Hz. If I were to try to move that closer, I could enter in, let's say, 800 Hz. And the capacitor we're using is 56 nano, then my resistor, let's say it's 3.6K. I don't know if that's a standard value, I'm just putting it in here to see what happens. So that would change our pole location a little bit, but it would move our zero in a lot closer. So we run the simulation with a 3.6K. Now double check these values, and it's still good up to 320 Hz, but again at 640 Hz, it's still a bit too steep, even though I brought the zero closer to this area to try to make it not as attenuated. So I found I was just getting nowhere. So I decided that's basically an extra zero. It's not doing me any good down in this frequency range. Let's move it out of the way then. And maybe I can use it later on in the filter. So up here, I don't know, somewhere between 3 to 5 kilohertz, we're really out of the zone of this response. Something around 5 kilohertz into this little scratch pad calculates a resistor of 568. So let's just choose a standard resistor of 560. So our pole moved again, it's 270 Hz, but now the zero is all the way up at just over 5 kilohertz. So we update the part values, run this, check the values, and again, we're still good up to 320 Hz. We're still kind of stuck in the same area at 640 Hz, being too steep just a little bit, but we've manipulated the location of poles and zeros so that they may work better for us later on. So we've done all we can with these first 3 stages. Since we know this is the final circuit that works, we might as well move on to this other capacitor. But if I were doing this blindly, I'd probably be adding another several stages here because it's all guessing. So with this capacitor here, there's no extra resistor, so it's basically a low-pass filter with 10K, and we need to figure out where we want to put a pole and figure out this capacitor value. And of course, we've got a lot to attenuate up here toward 20 kilohertz from where we're at, so maybe trying arbitrarily around 5 kilohertz where it really starts to flatten out. Let's add a pole there. So I'm using the transfer function for the phase lag compensator, and in that case, R2 would need to be 0 ohms because it doesn't exist. It's a straight wire. Somewhere around 4 kilohertz would let me use 3.9 nano, and that's where the pole would be. So we add 3.9 nano on this last RC filter and run it. And now we can see with this final low pass, we're just going to eventually roll off forever. There's no more flattening out with a phase lag. And now with these values, let's double check over here. Starting at minus 3.26 dB. Again, we get stuck at 640 Hz. It's got too much attenuation, but it's good up until then. So we're back to just looking at this and trying to figure out what we need to do here, moving poles and zeros around because we know this circuit should work. We just got to get the right values. If we take a look again at this second stage here and plug those values into the calculator, 1K resistor, 180 nano, that's where we have a pole at 80 and a zero at 884. If we're saying at 640 Hz we have too much attenuation, and a zero would start reducing that attenuation there, let's take this zero at 884 and try to move it down toward 640. And that should make it less steep because it's going to try to go back to being flat just by playing around with the values. If we make this 1.3K instead of 1K, our pole is still close to 80, so it's relatively unaffected for the slope. But our 0 is shifted now down to 680 instead of 880. So we change this to 1.3K and rerun. Double check these values starting at minus 3.26. And finally, 640 Hertz is within plus or minus 1 dB of our overall minus 3 per octave. In fact, we're good all the way up to 5.1 kilohertz now, and then it's not enough attenuation. It kind of just goes flat, as we can see up here. So we need more attenuation up here between this 10 and 20 kilohertz final section to try and get these last two octaves to roll off minus 3 dB each. So going back to this scratch pad where we put a pole for that final RC filter with a 3.9 nano targeting around 4 kilohertz, we should probably move that pole lower, and that means this final roll-off will happen sooner, and hopefully we can make the slope go deeper in 10 to 20 kilohertz. So let's just go on up to the actual equation here. If we make R2 basically negligible, we were at 3.9 nano for the capacitor on the RC. There's our pole at 4 kilohertz. And of course the 0 in a low-pass filter, it's very far away, so it's basically not part of our circuit. Now we can just play with this capacitor, the only value we can really change in the low pass, and we can just move this pole around. So let's see what happens. If we made that 6.8 nano, the pole would shift down to 2.3 kilohertz. So let's just try that. Check the table. It didn't really attenuate these last couple of octaves, so let's try moving it even lower. If we go 15 nano, we're putting it around 1 kilohertz. So that's going to be up here because it seems we need a more extreme slope. We're just kind of barely getting anywhere. So let's try that. 15 nano and check the numbers starting at minus 3.3. We're still not good enough at these higher frequencies. So at this point, I've attempted to move the poles and zeros around and I've filled in values for everything. It's still not quite right. In the area of 640 Hertz and 1.28 kilohertz, it's barely within spec of plus or minus 1 dB. I'd like this to be minus 18.33. It's minus 19.35, close enough. Then it starts getting okay again, and it's not right at the last two octaves. So the one thing that I can keep in mind, on this third phase lag stage, I did have that extra 0 I just kind of arbitrarily threw here around 5 kilohertz. And what that's going to do here, it starts doing this where it tapers off again. It kind of gets a little more gradual and shallow in the attenuation. And then we have this final RC low pass that really drops things off. So if I take that spare 0 and maybe move it further up a bit, it might make this gentle curve here go back to being more steep, and then this final low pass really makes it steep, further than we care about. So we might be able to get the attenuation correct, making it more steep further up. So let's try shifting that around. And since we're so close, I'm just going to do this empirically. By now, I know that if I make this series resistor a lower value, the 0 should move up in frequency. And it happens that if I make this 390, I just saw that this made this here a little steeper, and then that final filter really took over. So that's kind of what we were trying to do. Move the 0 away, allow it to attenuate more. So let's plug that into the calculation. 56 nano, 390, so our pole is relatively unchanged, and our 0 shifted up in frequency around almost 7.3 kilohertz. Checking the numbers, starting at minus 3.3, 640 is borderline to be within 1 dB of minus 18.3. The next one is also cutting it close. Then we want minus 24.3, and we got 24.9. and we want at the end minus 33.3, and we're within 1 dB. Done! Let's build this thing once and for all and do some measurements for the levels and compare it to what we're calculating here for certain frequencies. I breadboarded the filter using whatever capacitors I could find, and I had to put some in parallel to get close enough to the target values. To get an overview of the filter in action, just to make sure it's even doing what we wanted, I set up a sine wave signal generator in logarithmic sweep mode to take 1 second to go between 20 Hz and 20 kHz. So then, just looking at that on the scope, it's not a proper logarithmic vertical axis plot, but at least I can see that the signal is attenuating as frequency increases the way I want. So then I took some specific amplitude measurements at different frequencies to double check the exact attenuation at 20 Hz, 20 kHz to get the endpoints. And then 1 kHz is a very common audio frequency test tone, so I put a sine wave at 1 kHz to double check how it works in that range. With the input sine wave set for 1 volt peak, it's easy to calculate the dB attenuation of the filter because the dB level is 20 times the log of whatever the voltage reading is, and 20 times log of 1 volt is 0 dB. So all I need to do is actually take 20 times the log of each measured output voltage of the filter, and that's directly how much attenuation we have. This is working very well compared to the simulation. I think this circuit deserves its own dedicated PCB and can have a whole lot of potential future applications around the workbench. Stay tuned.